Hey, everybody. Ten folks in the chat. Good. And we're good there. All right. How's everybody doing? Good. Okey-doke. What's this here? Shrink that. Okay. Let me give this another minute and then I'll begin. Okey-doke. All righty. Let me get my screen shared here. I can do that. Yeah. Okay. All righty. Well, here we are. This is week 11, and we are almost through. We are almost done. So, there's not many things left for me to make you aware of, except you guys have a pending drop appointment for, I believe it is the 20, let's look at the modules here, the 28th, I believe. Let's see here. If we go to our getting started, I don't know if it was somebody in this class or not. Somebody said that they couldn't find the syllabus in the class. I don't know what to tell you, folks. It's right there in the getting started menu. I want to look down here at the bottom, I think. So yeah, withdrawal deadline's coming up in a couple of days. Okay. I don't think there's anybody. Now, there might be one or two people out of all 65 in this class that are in danger of, needing this in order to make their minimums for BFA or no, BA qualifications. If that's the case, don't forget it's Friday. Okay. So you can, of course, you don't get the refund on the tuition for the class, but you do get the, your grade won't count towards your GPA. So don't forget that. Other than that, we've got spring break coming up here in 2 weeks, it looks like, from the, what is it, the 14th to the, oh, I didn't put, yeah, here it is. I'm sorry, the 11th to the 18th. Okay. So that's coming up pretty quick as well. Just about 2 weeks, a little over 2 weeks. Okay. So just keep that in mind. And then after that, we've got like one more actual week of class. Then we have a study day, and then we'll have a final test, and we'll be out of here. Okay. So I just want to point that out so it's fresh in everybody's mind. And if you need that particular policy advantage or that withdrawal, then it is looming. Okay, so we're going to do color theory today. All right. Did anybody miss this assignment, depth of field as a compositional tool? because I don't remember if I mentioned it in my last lecture or not. I usually do when you've got an upcoming assignment, but it's there. Actually was due yesterday, so I had one person call me up and ask me for an extension. Other than that, I think it's been pretty quiet. So we're going to talk about color theory today, and this is pretty. I kind of like the concept of color theory. It's not too complicated. There's no math, no numbers involved. Some of you were really um, not enjoying the exposure worksheet, but this is more, well, there's some numbers, but they're not computational context. It's more like, understanding, kind of like degrees on a thermometer, maybe. Very similar to that context. So I want to talk to you about color in terms of the quality, the color quality of our lighting, the color rendition of our cameras, and how we coordinate that with our supplemental lighting that we do on film sets all the time. Okay. So right here, you can see this is an energized tungsten halogen household bulb, we call this structure here. The type of thing that you might find screwed into the lamps in your living room. Okay. And we're going to talk about something called Kelvin Degrees here this afternoon, which is going to help make some of this stuff make sense to you. I want to cover the visible spectrum, primary, secondaries, and so on, I call it, tungsten versus daylight, and then the Kelvin temperature scale. Some of the materials that I have prepared for this lecture have come from the Set Lighting Technician's Handbook. This is the most recent 4th edition. I have given you guys a PDF copy of the 2nd edition, which is, I believe, well, it's a little dated in that it doesn't have much on LEDs contained in it. I know I have a PDF copy of this edition somewhere. I have not been able to locate it, so I gave you guys the next best thing. The 2nd edition will cover everything up to the LED paradigm shift that we've experienced here in the last few years. But in terms of other practical reference material, this textbook will, the textbook I've given you, I should say, will be relevant. The conversation about color science is relevant. In all the other aspects, the 2nd edition is completely fine for your consumption in terms of reliable information. The visible spectrum, what is it? Okay, this is what we associate with the visible spectrum. Okay, it's all the hues from a bright red to an ultraviolet. And if I'm not mistaken, yeah, this is actually, I hate when they do this, these textbooks, they reverse the visible spectrum. The ultraviolets technically should be on the left. And I'm going to show you why in a minute. But this is the range of colors. Some people refer to it as the rainbow. But this is the range of the visible spectrum, okay, from violet to bright red. These are the frequencies of color that we can see with our human eye as extracted from the total electromagnetic spectrum, okay? So what is the electromagnetic spectrum? Well, this above here in this graphic represents the entire electromagnetic spectrum. It's going from long radio waves at the extreme right and what we call, not gamma rays. Yeah, I think these are gamma rays at the extreme left. And then X-rays right next to it. The electromagnetic spectrum. So this is a radiation spectrum. Okay, it's all of the frequencies of light, including the visible spectrum. So there's a lot that we don't see. We have X-ray devices. Obviously, if you break a leg or an arm when you're skiing, you go and get an X-ray. We have the UV spectrum, which can be used for a number of medical applications. We have the IR spectrum, the infrared, for which we have films that are sensitive in these frequencies. Microwaves, we know what those are for. And then FM and AM radio waves. And then we have some of the longer waves that we can use for communication on a variety of different bandwidths for police, for marine, for walkie-talkies, for wireless microphones, things of that nature. Okay, so there's a great deal of the spectrum that we can't see with our eyes. So we only deal with this tiny chunk right here, and it's roughly from about 400 to 700 nanometers, plus or minus a few. Okay, so that's the whole visible spectrum right here. A little under, for about 360 to about 720 nanometers. Okay. Wavelengths of visible light. Okay, this stretches all the way back to Isaac Newton. So in 1665, among other things that Newton used to study and tinker with, he found a pair of prisms, and he found that if he held the prism up to a beam of light, like a shaft of sunshine coming through a window, that he could separate the visible white light into its component parts. Okay, and he experimented with this considerably before he brought it to his contemporaries, who scoffed at the concept that white light consisted of, or was composed of, a variety of different color frequencies that when combined equaled white light. So what he did is he paired up two prisms, and he opened up the white light to its component frequencies with one prism, and then with the other prism he reassembled the colored spectrum back into white light, thereby creating a live demonstration for his peers that basically what he theorized was true, that white light consisted of individual frequencies that when combined equaled white light. Here's a quick video from a NASA film that I was looking at that talks a little bit about that.
All electromagnetic radiation is light. Visible light is the only part of the spectrum you can see. For all your life, your eyes have relied on this one narrow band of EM radiation to gather information about your world. Though our sun's visible light appears white, it is really the combined light of the individual rainbow colors with wavelengths ranging from violet at 380 nanometers to red at 700 nanometers. Before Isaac Newton's famed experiment in 1665, people thought that a prism somehow colored the sun's white light as it bent and spread a sunbeam. Newton disproved this idea by using two prisms. To show that white light is made up of the bands of colored light, Newton used a second prism to show that the bands of colored light combine to make white light again. Visible light contains important scientific clues that reveal hidden properties.
Okay. It goes on to talk about how we can use these values that we analyze in the spectral qualities of light to figure out the compositions of stars, to figure out the gases present in celestial bodies like planets and so forth. There's a lot of applications that we can use the spectrum for, but for our purposes, we're really just talking about what we can see and how our cameras render that light and how we can use that light to our dramatic narrative ends purposes. So within the visible light spectrum, EM radiation, by the way, is nothing more than electromagnetic radiation, referring to the total spectrum, What we're concerned with is the visible spectrum of light. Okay, there is a difference. Okay, so each visible color in the spectrum has a frequency, and it's measured in nanometers. Nanometers are very, very small degrees of measurement, and they describe the length of the undulating wave that represents the frequency of that color. So different colors have different frequencies, shorter waves or longer waves. Okay, and they kind of work just like waves in water, right? So waves that crash on the beach and give us terrific surf to go surfing with are high frequency, short wavelength waves. Tsunamis and big waves, even hurricane waves and things like that out in the middle of the ocean have very long frequencies, and they roll with very long troughs and very high peaks. And those represent wider, longer frequencies. And color kind of works the same way. If you look at this chart here, you can see that the violet frequencies and the blue frequencies have very, very compressed peaks and troughs. Okay, so if you're going to look at a wave, you have a peak, you have a trough, and then you have the frequency is the number of waves in a given measure of time, right? And then you also have amplitude, so that'll be the intensity of the wave. So if these waves had the same frequency and the same sort of interval, but they were really spiky, that would just mean that they were really, really dense saturated colors. Okay. So this one's showing us 400 to 700. It's a little bit shorter than that, a little bit about 360. I've put two red carets here on this same graph. It's the same one we were just looking at, to indicate to you something very, very special that's relevant to what we do all the time, which is chroma key work. So the visible frequencies marked with red arrows designate the values that we use for chroma key replacement. Okay. Blue screens and green screens, folks. That's what this is all about, right? So right here around, I don't know, 460. Man, this might be a little bit of a generous placement on this particular caret. It might have to actually be about here, but somewhere around 460 and right around 550 for green screens. Okay. And this is significant in such that your software, for instance, that you use to cut in on your green screen replacements will key on those frequencies, which is why it's really, really important for us to get the right color screens and have them lit fairly evenly as we can get them. Okay. In the old days of photochemical replacement, shadows were difficult to work around in terms of photographic green screen replacement, because we were using a series of films photographing different layers and then putting layers together, and we could create shadows in our background plate from shadows that were present either on our green screen or on our element itself. Okay. And so that was probably an undesirable result most of the time with shadows. But it also has to do with color frequency, right? So if you can keep the screens fairly even when you light them, then the computer's replacement software can key on the proper frequencies of blue or green and make sure that it lifts only those values out of your footage. Okay. So if you have other values of green, say, that are mixed with other colors or tinted in some way, that will change the frequency of that hue of green, and it will fall outside of the criteria that your software is using to make a green screen replacement. Okay. But wherever possible, you want to avoid using an excess number of shades within the same color, either green or blue, when you're doing chroma key replacement. But this is where it falls on the spectral chart right here, blue and green. So we need a way to refer to color in a photographic sense, and it's going to be the same standard that our cameras are going to use when we refer to color. And we're going to be concerned with two primary colors, and it won't be blue and green, but it'll be blue and orange, and I'm going to explain to you why. But as objects grow hotter, and by objects, the standard was created with a 1 meter bar of steel. But when objects grow hotter, they radiate energy, dominated by shorter wavelengths, changing color before our eyes. A flame on a blowtorch shifts from reddish to bluish in color as it's adjusted to burn hotter. Okay, anybody ever use a sweating torch to put together copper piping, or to get a stuck nut on an engine block or anything of that nature? You fire that thing up, right? And as you tweak the flame to get the right length and the right color so you can sweat with it, it gets bluer and bluer and bluer. It's blue hot, right? It's extremely, extremely hot. And that's the heat, the kind of heat we need that will either melt our lead solder, or enough heat that will take two stuck pieces of competitive metals, steel and aluminum maybe, and get the steel to expand and unseat itself from, say, an aluminum nut or an aluminum bolt in a steel engine block. Okay. So we're going to use something we call the Kelvin temperature scale, and it was developed a long time ago. There was somebody named Kelvin somewhere back in the history of this whole thing, and that's not really relevant to the conversation. What is relevant is that the Kelvin scale is what we refer to as a temperature scale, and it does have to do with heat, okay, but from a certain point of view. So Kelvin is a temperature scale designed so that 0 degrees as a reference is defined as absolute zero. And at absolute zero, this is a hypothetical temperature, by the way, because we haven't been able to achieve it. But in theory, at absolute zero, all molecular movement stops. That means the spinning of the nucleus, the orbiting of the electrons, everything, all movement stops, right? And that would be kind of a disastrous position for an atom to be in or a molecule to be in. But absolute zero, all movement stops, okay? All actual temperatures are above absolute zero. So everything that we know, even the coldest cold, is far higher than absolute zero, okay? And the size or the increments used to describe those degrees are in Celsius, okay? But when we're talking about the Kelvin scale, extremes of temperature outside our normal realm of hot and cold, we use the Kelvin scale, okay? So Kelvin is used for pinpointing color temperature as it's typically used in lighting. In a lighting application, Kelvin temperature represents the color temperature such as white, blue, or red as it relates to the physical temperature of that object. So for instance, the original experiments done by the folks at, I think it was Oxford University, took a 1 meter bar of steel and they started heating it. And they had the ability to superheat it, okay? Does anybody know roughly the temperature that a light bulb burns at? It's pretty high. It's pretty high. It can range anywhere from about 1500 to about 2500 degrees. And at 2500 degrees, you have to be able to make that light bulb out of components that aren't going to melt under that kind of heat. Just as a reference, lead, I think, melts at about 700 degrees. So you can't make light bulbs out of lead, right? That's why we use specific materials in light bulbs that can withstand the high temperatures of burning and ignition, high enough that cause illumination to be practical or useful to us. You can use a lighter, and that flame's not terribly hot in retrospect, and it'll light a little bit of the area. But if you superheat a bar of steel to 3200 degrees Kelvin, that bar of steel is going to radiate with a brilliant orange color that's going to be bright enough possibly to light your entire immediate area, okay? Do you ever see photographs taken in a smelt or in a steel factory where the guys have the special cameras that can photograph these super bright images of the molten steel being poured into the molds out of the smelts and out of the oh gosh, I forget what they call the big vessels where they melt the stuff down in aggregate, right? But that's all, those exposures are all made with the brightness of the molten steel coming out of those vats, okay? So we're discussing superheating something to the point where it actually radiates usable amounts of functional light, okay? And the first color that we're going to encounter is going to be the red frequencies, the longer wavelength frequencies. They're lower in temperature value, but oddly enough, because of their physical appearance, we refer to them as warmer colors. Warm as opposed to hot. Hot colors are more white, okay? Just coincidentally, if you look at these spectrums here, look at the red spectrum here, the warm spectrum, as opposed to what we would call the hot spectrum, okay? Red's all the way on one end, right? The portion of the Kelvin scale concerned with film and video lighting is represented below, and it's an approximation based on hue. The range of color starts around 2400 degrees Kelvin, and it represents the hue that's associated with warm interior lighting. So I put a little light bulb over here to give you a sense of what end of the spectrum this is. So Have you ever stood outside of your house at night and looked up at the sky and you're looking up at the moon, looking up at the stars? Maybe it's right after dusk, right? And the sky is a real deep blue, and it graduates into black where night is approaching and we're heading into the dark hours of the evening. But you turn around and you look at your house through an open window, and the environment inside the house looks really orange to your eye. Have you ever seen that? Or you go out walking in the neighborhood late at night and you're walking under the street lights, which are either mercury vapor, which are an intense blue-green color, or sodium vapor, which is a yellow color. But when you look inside the houses, inside the windows that you're passing as you walk down the street, the environment inside looks very warm and very orange in color and very kind of snuggly and inviting, right? That's the color we associate with interior lighting. It's the color that's generated by a light bulb that's burning somewhere between, say, 2000 degrees and 3000 degrees Kelvin. It's this warm end of the temperature scale here. Okay. So when you think about interior lighting, think about orange in color. Now, conversely, when you think about exterior light, you don't really associate exterior light with blue, do you? But again, have you ever been sitting maybe in your living room at dusk and you notice after the sun has gone down, not before, but after the sun goes down, that everything inside the living room seems to be normally color balanced to your eye, but the light outside the window has a real blue quality to it. Did you ever notice that? Okay, so that's the reverse of the frequencies working on your human eye. So what our human eye is doing in whatever environment we're in is taking the available light in whatever color it happens to be radiating at, and our brains tell us to adjust to that color frequency as normal, right? So we don't see necessarily a color cast associated with that light until another source is introduced, either through a window or through a fixture or through a device like a cell phone, all right, or a laptop screen that's adjusted for daylight frequencies. The minute we introduce a different competing frequency, immediately our eyes will sense and try to adjust for the change in some way. Okay. So our eyes are doing things for us that our cameras cannot do. Well, technically, I shouldn't say that anymore because we have auto CCT adjustments for these cameras, but it's not an ideal way to operate your cinema camera. So when you operate your cinema camera, you're going to have to tell that camera what color frequencies you're working with. Are you outside in daylight, or are you inside in interior light? And interior light is what we refer to as tungsten light, because tungsten is the metal inside the light bulb that we use to burn at intense heat and radiate that orange light out of the light bulb. Okay, so we call that kind of light interior tungsten. And you'll see that I took this scale off of a fluorescent tube replacement. Okay, a fluorescent bulb that was designed to replace an older eco-watt style bulb that had a real green, spiky color quality to it. You know, do you remember years ago, maybe your dad had shop lights in the garage, and when you go out in the garage at night, maybe he was working on a workbench or working on the car or something, and that light always had kind of a weird sort of headachy green quality to it. Not right, because the minute you'd leave the garage and go back into the house, your eyes would relax into the warm tungsten light and feel, you know, much less stress on your eyeballs. I don't know if you, but that's the original green fluorescent color spike that we had to work around as filmmakers 20, 30 years ago with colored gels and with specific camera settings. Okay, nowadays we can get color corrected LED replacements, fluorescent replacements, and we can take all those old, crappy old sources that had lousy chemistry and replace them with units that will burn at more reliable color temperatures, and they'll pick a range. So if you go to Home Depot and look at, say, LED replacement bulbs, you're going to have your choice. You're going to have your choice of a tungsten LED replacement bulb, or a daylight LED replacement bulb, or a warm white and a cool white. Sometimes they'll use those terms interchangeably. Cool white referring to more daylight balanced Kelvin degrees, and warm white, more tungsten balanced Kelvin degrees. And the difference will be, well, they're asking you a simple question. Do you want your interior lighting to be more orange or more like outside, more bluish, more whitish? And then you pick the bulbs that you're most comfortable with. A lot of folks, myself included, because I was born in the age where tungsten bulbs were prolific, and there was, at best we had those crappy fluorescent replacements to put in our lamps, which gave the room a really sickly color that you didn't want to read by or be in doing any kind of work that would require that you perceive colors accurately, like painting or doing arts and crafts or whatever. Lights were orange in color for me when I was a kid. So all the LED replacements that I've chosen for my house are tungsten value replacements, and they have that orange, sort of warm white quality to them. You can see the range of colors of all the different choices you can pick from it, like say Home Depot, for instance. You got your warm whites at one end, you got your day bright or daylight, they call it, which are your neutral frequencies, neutral according to the lighting manufacturers. And then you got your bluer end of the spectrum, which represent your daylight balanced color sources. So let's say you had a really nice kitchen with a huge bank of floor to ceiling sliders, or bay windows or something, or a dining room with that kind of beautiful vista window structure where you got a lot of daylight cascading through the windows, right? On some days that's enough lighting for you to maybe to eat by or have activities in that room. Some days the light might not be as bright, or it might be later in the day where the sun's maybe on the other side of the house and you're not getting a whole lot of available light coming into the window. So you turn on the lights in the dining room, right? Well, if you turn on the lights in the dining room and they're tungsten balanced, there's going to be a color cast. You're going to have sort of blue colored light coming through the windows, and you're going to have orange colored light coming down from, say, the recessed lighting. Well, you can choose to load them up with the blue end of the spectrum as opposed to the orange end of the spectrum, and put all the recessed lighting in your dining room balanced for daylight, so that whatever is coming through the windows is supplemented by your artificial lighting from overhead, so that you don't get any competing color contrasts with the light that's coming through the window. Some restaurants will do that so that the presentation is good for the diners who are looking at the colors of the food and the presentation of the food. They don't want the food to be perceived in any kind of strange coloration that might look like it's underprepared or improperly prepared, undercooked, whatever, right? So they want the same kind of colored lighting in the artificial sources as is coming through, giant windows that might be right next to your dining table. Okay. And this is an actual thing. So architects and restaurant designers, retail store designers, a lot of folks are concerned with these principles, and they play with these variables to affect your experiences at these places of business, whether it's a restaurant or a store where you're shopping for clothes, for instance. It's really important when you shop for clothes or makeup to understand what environment you're going to wear that makeup or wear those clothes in, and then make sure that the lighting in the store matches the situation you're going to be in, right? Hair and makeup people on a movie set a lot of times will ask us for some of our show lighting to light a corner of the stage where they got a makeup station set up, or in the hair and makeup room. A lot of studios will put crappy old regular fluorescents in the hair and makeup prep rooms, outside of the soundstage, maybe down the hallway. And it's the wrong color lighting for the sets that are on stage. So they'll ask us for some tungsten lighting from our lighting package, so that they can light the makeup room in the same color of light that that the actors are then gonna come into the stage and be working under. Okay, so it's very important that there is an actual visible difference between the environment you're gonna be in and the color of the lighting that you're gonna use. So this is at the root of the discussion today. That's what we're talking about, is just the awareness of these differences and what they represent. Just as an FYI, candles burn at around 1900 degrees Kelvin, which is way below our warmest artificial lighting. If I go way up here, let's see where the visible spectrum was. So it's up here in these really long frequencies. Okay, somewhere way up here. Okay, at the end of this spectrum. Okay. Just as an FYI, 1900 degrees Kelvin. In other words, really red. Okay. So even if you have your camera set to 2500 degrees Kelvin, which is usually the lowest a lot of these cameras will go, your candles are still going to look really warm in color on film. Okay, because they're well below the normal limitations of what we normally want to adjust for. So it's good to know that if you're going to use candles as your main source of lighting for a film that you're going to do. So CCT is something we want to talk about. And all CCT is it's an acronym for what we're talking about: corrective color temperature. Okay. CCT is what we refer to this concept we're talking about. Okay. Color balance. Color motion picture films are designed to reproduce colors accurately when lit with fixtures that have particular color quality or color temperature. Okay. So let that sink in for a minute. The color component of a light source is quantified by its color temperature, or its CCT. Since tungsten filaments burn most efficiently at a color temperature of around 3200 degrees Kelvin, tungsten balanced film stock is designed to reproduce colors accurately when the subjects are lit with tungsten balanced film that's balanced for 3200 Kelvin. Same situation with the makeup, all right? If you're going to photograph subjects with motion picture theatrical lighting, okay, that lighting is going to burn most efficiently at 3200 Kelvin. So the cameras have to have a preset, if it's digital, for 3200 Kelvin, so that when you look at a swatch of white, like if you look at a white paint swatch or a sheet of paper, and you photograph that sheet of paper under tungsten lighting, if the camera is balanced correctly for the lighting we're using, that sheet of paper, when you look at it projected or when you look at it on playback on your TV monitor, will appear white, not orange and not blue, white. Okay. That means that your camera's color sensitivity and your lighting, the CCT of your lighting, were in balance. Okay. If you take that same sheet of paper and you have your camera adjusted for 3200 Kelvin, but you use a light fixture that is daylight balanced, and that Kelvin temperature can be as high as 5600 Kelvin or higher. When you project that film back or you watch that on a monitor, that sheet of paper is going to appear slightly blue, tinted blue. Okay, not a heavy blue, but a subtle frequency of blue. Okay. Today's modern digital cameras can be adjusted to be sensitive to a variety of color temperatures, but the two presets that we always insist that we have are 3200 and 5600, because 5600 is the color temperature of daylight, 5600 Kelvin. That's our benchmark. Daylight can be a little bit cooler than that. It can be 5000, it can be 4800, it can be 4500. All right, depending on the angle of the sun in the sky, depending on whether it's a cloudy day or a clear day, whether it's summer or winter, okay? And daylight can be as bright as 10 or 12,000 degrees Kelvin on a really bright, clear, sunny day in the midsummer at noon in the shade under a big leafy tree. Okay. So daylight is a little radical in its expression of color temperature in that it can range anywhere from 4,500 to 12,000 degrees Kelvin. But we can't really plan for all of those different contingencies. So we pick a benchmark and we say that daylight is 5,600 degrees Kelvin. Okay. 5,600 degrees Kelvin. When the camera is set to 5,600 degrees Kelvin and you shoot under daylight, that white sheet of paper will again appear balanced, normally or naturally white, not orange and not blue. Okay. Again, the camera will be in color balance if it's set to 5,600K on the camera and the lighting you're using is color qualified at 5,600 degrees Kelvin. Okay. I'm going to show you a couple of different styles of lights that work this way. And they're lights that you're going to see on a regular basis from here on out, whether it's here at school or whether it's out in the industry. If you gain access to the industry and you start working on sets, you're going to see this type of lighting from here on out. Okay. What are we talking about? We're talking about motion picture lighting. And we're talking about these apparent differences in hue that we see all the time on the screen. And it's not random. Okay, it's deliberate. And there's a few reasons why. Warm colors are said to advance in the frame. Cool colors are said to recede in the frame. That's one principal reason why we're concerned with color in motion picture lighting. You see how this person is lit and she's got a prevailing orange tone on most of her face? And then part of her face over here is what we call edge lit with a bluer shade, a bluer hue. Blue colors recede into the background. This is called an edge light, and most of the time we'll use bluer colored lights as edge lights, especially for night exteriors, okay, in a traditional setting to indicate that it's coming from the larger world somewhere behind the subject. The world writ large is creeping into your frame in the form of an edge light coming from behind this person. And we signify by using an edge light that's blue in color. And then the key light is warmer in color in reference to the background light. The background will also be lit bluer than warmer because of the idea that cool colors recede. And we want the background to be in the background. So foreground lighting in a motion picture set will be warmer in tone. Background light will be cooler in tone so that we get a separation there of foreground and background. And then the middle ground will usually be balanced to neutral, right? Sounds like something else we talked about not too long ago. What's it sound like? You're nodding your head, Gabby. What does it sound like?
Depth of field.
You got it. Depth of field, right? What is this all about? This is about creating dimension. So that means that you can create a sense of depth, a sense of three-dimensionality by which colors you use psychologically to illuminate your subjects. Subjects that are doing things in the foreground, in other words, really close to camera, will probably be warmly lit. And subjects that are functioning in the background, maybe even in the same frame, will have bluer light lighting them so that we can create a sense of depth between foreground and background. This whole medium that we're talking about, film, and by association, digital media, which is digital film, digital cinema, it's all about creating the illusion of three dimensions with a two-dimensional medium. Okay, we have length and width in motion pictures, but we don't have depth as a physical dimension, right? We don't watch, well, we have 3D movies, sort of. But for the most part, our traditional experience is two-dimensional. So how do we give the sense of a third dimension, if not with depth of field, lenses with field of view, and colors that separate foreground, middle ground, and background? Okay. There's also certain psychological effects that color have on us as viewers. So I'm going to talk about that last. There's a color psychology associated with all of these hues, and we pick them based on how we want our audiences to feel. Okay. But for the most part, suffice it to say that warm colors for key lighting are psychologically more acceptable to the human psyche than cooler blue colors. Cooler blue colors are something that psychologically we don't respond as affirmatively to as warm colors. Okay. And that has to do with the color science of our eyeball and how our eyeball actually works. But I want to get off that topic for a minute, and I want to just talk to you about what are the kinds of fixtures that we work with in motion pictures that give us these advantages of predicting color output and balancing with our cameras. And there are a lot of them. There's way more than that are pictured in this photograph. Okay, this just happens to be the ARRI system of lighting, and this photograph from ARRI doesn't even have everything they offer. And it's also this photograph about probably 20 years old. It's out of the ARRI catalog, and it doesn't have the new ARRI soft panels. It doesn't have any of the large ARRI HMIs, the 12,000, 18,000 watt, 24,000 watt lights. But this is a lot of lights, and each one of these lights has a different quality about it that ultimately you will grow to understand in differences. Let two folks in real quick. Sorry about that. Okay. Some of these lights are balanced for daylight output. That's these lights up here. And looks like these lights here, this upper corner of stuff right here. And possibly this fluorescent fixture down here, these two guys down here. All these lights on the bottom are all balanced for 3200 degrees Kelvin, except for possibly these three right here. And then these lights over here on this side are also balanced for 3200 degrees Kelvin. Okay, so we have outdoor lights and indoor lights in a motion picture lighting package, and we use them based on what used to be based on the color film stock we were shooting. Now we do it for the psychological reasons. We do it because the cameras can balance one way or the other. Okay, and now we use them to create these mixtures that'll give us these dimensional added advantages of creating depth with warm lights in the foreground, blue lights in the background. So now we're using all of these at the same time in any particular shot with a higher degree of complexity than we ever used to do in the old days. If you had to know the color of the output out of one of these fixtures, there's a couple of different ways to do it. The first would be to use what we call a mass spectrometer. Okay. I have one here. What a surprise. And basically what this thing will do is render something like what you see here in these two windows on the screen right now, which is the spectral readout of a particular lighting fixture. If you look at the data in these windows here, look at CCT right here. This CCT says 5,588. What color light is this?
Exterior daylight.
What color is that?
Blue.
Blue. It's a blue light. Look over here. CCT 3225, 3,225. What color is that light?
Orange.
It's orangish, yeah. It's a tungsten light. This is a tungsten balanced LED light that I was testing and vetting for the student lighting kits over at Los Angeles Film School. This is a daylight balanced fixture. Actually, these are both from the same fixture that was switchable, one or the other, because it was LED. So it had LEDs that were tungsten balanced mixed with LEDs that were daylight balanced on two different circuits. You flip the switch one way, it burns orange. You flip the switch the other way, it burns blue, right? So you could use the same lights inside or outside, and you could balance them three ways. Everything on to give you a median color output, which is neutral 4,200 degrees Kelvin. Orange balance for inside work, or blue balance for outside work. Okay. And you can tell what color these lights are two different ways. You can look at the CCT value and understand that the CCT value, if it's in this range, the 3000 range, it's an orange colored light. And the CCT value over here in the 5000 range is a blue colored light, daylight and tungsten. You can also look at the graph itself. And you see how all the colors of the visible spectrum are present on that little histogram? But there's one particular peak that's higher than the others. In this one, it happens to be the blue peak. And in this one, it happens to be the orange peak. And that peak corresponds with the CCT value over here. So I can take a light on a set, and if I'm not sure what color it burns at, I'll take my handheld spectrometer and I'll tell it to show me a spectrum. I have all these different choices. I'll say, show me the spectrum of the light I'm going to read, and it's going to give me a grid. And then I'm going to take this instrument, and I've got a little actuator button here, and I'm going to stick it right in my light source. So I've got a key light over my head right now. It's an LED light source. It's the only source in the room. I've got a window over off to my right, but the shades are drawn, so there's really nothing coming through that window right now. But I'm going to take my spectrometer and I'm going to put this little white disc pretty close to where the full output of this light is blooming from the front of the fixture. And I'm going to actuate it. And then I'm going to take a look at the spectrum that resulted from that reading. And look what I got. You see that little symbol right there? That's a lambda symbol. It's the prevailing lambda value, the same as these high peaks on these histograms. This is called the prevailing lambda value. All right, and this one's telling me the prevailing lambda value is 453 nanometers. What color is that light balanced for?
Blue.
You betcha. Let's go back and look at it. Here we go, right here. 453 is about right there. It's real blue. And it just so happens that I have my laptop set to balance for that light so that I don't have a real strange color value to my skin tone. It's a little bit warm because I have the laptop set at about 6,000 degrees Kelvin, okay, which is one of the Apple presets for your monitor output, right? So that if I'm working under daylight, if I'm outside at a picnic table, or if I'm working under daylight balanced lighting at 5,600 Kelvin or 5,000 degrees Kelvin, and my screen or my camera is set for 6,000, it will see that light as just slightly warm. And just slightly warm means I'll have a normal cast to my complexion. I won't look too white and too sickly, right? I'll have a nice kind of you know, not a golden tint, but a warm tint, slightly warm tint that makes me look normal, you know, healthy looking, right? And that's the science and the logic behind colored gels that we'll talk about at some point. Okay. But it's all about balancing. It's all about the presets of our devices. In this case, I have a camera that's set to 6,000. I have a light that's set to 5,600. That aggregate result is slightly warm, so my skin looks fairly normal in terms of color balance, right? And it's all in the 453 nanometer frequency range. and you can see the actual graph, you can see that big prevailing lambda spike is in the blue. See that? And all this is cut off real flat right across here, because this is a high frequency light output that is, we call it square wave. In other words, if I wanted to shoot at really high camera frame rates and stuff, I could do that with this light source, because it has been trimmed out to where it won't fluctuate in intensity when I change the frame rate of my camera, which some lighting will do. Okay, just a FYI. It's kind of off script, but I thought as long as I'm here, I might as well tell you what that flatness means. Okay, so tungsten light and daylight include every color across the visible spectrum. So you can see that these little histograms have all of it: green, yellow, orange, red, blue, purple, right? We want our light sources to have this kind of color quality because it's what we call full spectrum light output, okay? All colors are made up of a mixture of the colors from the visible spectrum. Very few things in nature are pure frequency tones, right? So when a camera sees a frequency that's a spot on frequency, that's the kind of color we like to use for our chroma key replacement screens. And the easiest ones for our eyeballs to see are green and blue. We have a very high tolerance for warm spectrum light output. Psychologically, our brains will accommodate a huge amount of difference in color accuracy between warm hues. But we can immediately see, psychologically and physically with our eyes, we can immediately see the slight difference between a blue and a green value. That's because of the way our eyes are built and the rods and cones inside our eye and how they're biased to detect certain color frequencies. Okay, so colors at one end of the spectrum, our eyes are very tolerant for differences at this end of the spectrum and very intolerant for color differences at this end of the spectrum. It just so happens that those crappy old fluorescent lights that your dad used in the garage to work on the car had a lot of green color value present in the output spectrum and very little blue and almost no orange frequencies. There were gaps in the spectral output of that light source. And as a result of that, our eyes detected the old time fluorescent lights as an ugly, impure color output, which gave us headaches and made us depressed and made people not want to work in offices and things of that nature. I don't know if you're aware of these types of social phenomenon, but it used to be that people who had office jobs and stuff would suffer from anxieties and depressions and headaches and migraines and things of that nature. And a lot of it had to do with the kind of cheap environmental lighting that they were being forced to work under, which is a lot of the reason why we have such sort of high-end office designs now for people to work in these office environments, because we understand more about these types of things as the years pass. And psychologically, people have to work under full spectrum lighting so that emotionally and psychologically we don't develop anxieties, because our eyes are working in an environment where we don't see all the colors present outside. Okay, people get snow depression, they get the winter doldrums when they live in countries where it's cold a lot of the time and overcast a lot of the time. Do you ever notice on an overcast day how everything looks kind of bluish? Because there's no raw sunlight reaching the ground, right? It's getting filtered through clouds. Okay, long frequencies getting filtered out through the clouds, leaving only the blue, the bluer light hitting the ground at ground level. And so we end up in a world where everything has a different color value. It's all the same. And we start being, it's hard to gauge our depth perception, and our attitudes will shift. Okay, there's a lot of psychology to color science and the way our brains perceive and look at light. Okay, so what's nice is to have fixtures that have full spectral output, meaning all the colors are represented in their proper proportions, and then there's a prevailing value, either orange or blue, that we can balance our cameras for and our lighting with, and we can get nice neutral values out of our lighting and register on our films. A traditional light bulb is sort of built like so. You got a base, screws into your lamp next to your sofa in your living room, right? We have the center column or the post with positive and negative electrodes inside. We have a filament. The filament is what's actually going to pass high current through, and it's going to glow, and that's going to produce the light. And this filament is made out of tungsten metal. Okay, this business right here. In fact, I think the whole business is made out of zinc and tungsten. Okay, and this is the part that's actually going to pass the current through a household current passed through a very, very thin wire creates a high amount of resistance in the electrical flow. And the resistance causes friction, and the friction causes the tungsten metal to get very, very hot and burn brightly. And that's where our output from our lamps comes from. Okay. Contemporary theatrical lighting, like some of the stuff I showed you in this picture here, use a sophisticated technology. It's also using tungsten filaments. You can see in here a very complex tungsten filament inside the bulb jacket. The bulb jacket is the glass vessel where the filament is contained. Inside the gas jacket is halogen and a mixture of a couple of other rare earth gases that create a process inside this light bulb. When your household lights burn, anybody still have tungsten household bulbs in any of your lamps at home? And so you've changed the bulbs from time to time, right, in the lamps? When you pull the dead bulb out, what does it look like? Did you ever notice it kind of looks like there's a dingy black film on the inside of the light bulb?
It looks burnt on the inside.
Yeah.
Kind of like the fuse is burnt.
Yeah, that's basically exactly what's happening. What's happening is this filament is getting superheated. Without halogen gases inside the bulb jacket, the metal as it's burning is giving off exhaust, and the exhaust has, microfine components of the actual filament contained within it, and it will build up on the inside of the light bulb as a dingy black film. And that's how your mom used to be able to look down into the top of the lamps next to the sofa and be able to sort of get a sense of when those light bulbs needed to get changed. The more black dingy stuff was built up on the inside of the bulb, the closer it was to burning out and dying. And then you'd go and put a new one in that was nice and clear, and that would last 6 months or so, and then you'd have to change them out again. In the theatrical bulbs, the halogen gas, what it does is it latches onto that soot that's burning inside the bulb, and it kind of changes it chemically and makes it re-adhere to the light bulb when the light bulb's turned off and starts cooling down, so that it almost like it reinvigorates or renews the filament inside the bulb. And that will extend the lifespan of that bulb and also help it through a combination of gases burn at a predictable color value of 3200 Kelvin. This light bulb burns at around 2400 degrees Kelvin because there's no rare earth gases and halogen inside controlling the color output. It's just raw black body radiator, we call it. This thing heats up to the point where it glows red and orange, and the output of the light is thus. This one has those gases inside, burns very brightly at 3200 degrees Kelvin, so that our film stocks or our digital cinema cameras can balance to the output and create white light using these fixtures. Okay, I put a little bulb here to indicate that this is a tungsten balanced bulb. If you look on here, this one's made by Osram, and it's got nice IDs printed right on it. So it says Osram FKW. That's the style of bulb, FKW. It's a dual pin push base. One pin is a little thicker than the other, and the wattage or the output of this bulb is 300 watts at 120 volts. Okay, so in other words, the fixture that uses this bulb Has a plug that you can plug right into the wall in your house, and you can use it to film in your living room if you wanted to, or on a soundstage at Sony. It doesn't matter. It just needs 120 volts. It'll output 300 watts out of the fixture, which is a decent amount of output. It's a standard amount of output, predictable value, and it's orange in color. And so we have all that information printed right on the bulb shank. And the higher the wattages go in these bulbs, the more they will take on different forms. These bulbs, I have a lighting truck that's out in Christmas, Florida in storage, and I don't have any of my high voltage, high wattage bulbs here at the house, but essentially a bottle of bottled water, okay, like this one, this is the same size as this bulb here on the far left, minus the shank on the bottom. So there's another little bit of ceramic base and two large positive and negative anodes sticking out of the bottom of this thing. It's a giant push pin based bulb about the size of this bottle of water, and it burns at 5,000 watts of output, balanced color wise to 3,200 Kelvin. It's orange in output. It's what we call a 5K bulb, 5,000 watts. Okay. This here happens to be a 2K, 2,000 watt bulb. It's a little bit smaller, and then a little bit smaller again. This is an EGT bulb. It's a 1,000 watt or a 1K bulb. This little guy here at 300 watts, realistically, I used to have one here on my bench, but it's about the size of my LED flashlight versus the 5K bulb. The difference in size is matched by the difference in output. Wattage, 300 watts, 5,000 watts. Okay. And they fit into specialized fixtures. You guys got some of these laying around at UCF still, the incandescent or tungsten balanced fixtures. A lot of the stuff now we've replaced with LED fixtures that do the same things as these tungsten balanced fixtures, but they're much more efficient electronically. Okay. And I'm going to talk to you guys more about that when we do lighting. I think it starts next week when we do 3-point lighting. I'll talk to you about the difference between the power necessary to operate LEDs versus these incandescent bulbs. But suffice it to say, you can pull a lot of current from a source using incandescent or tungsten wattage lighting fixtures. Okay, they draw a lot of current from a source to the point where some guys in Hollywood have a full-time job working 10 to 12 to 14 hours a day, doing nothing but providing power on the ground on location sets for movies to shoot at. In other words, just laying down a portable power system so that the shooting crew can plug in their fixtures and operate their lights on location. Okay, it's a full-time job for some of those guys because the amount of power that these lights need is enormous. It's enormous. One of the nice added values of the LED lighting was stuff can run off of batteries. It's low voltage, low wattage, but with equivalent outputs that are similar to what we have here. Very functional at multiple color temperatures, so you can set them at daylight or tungsten or anywhere in between. And the thing about incandescent bulbs, because this thing has to heat up so that the filament gets red hot and emits light, logically, what's that going to tell you about the fixture that it's contained in? Light's going to get hot. Anybody have a tungsten desk lamp, either in your dorm or at home? And you go to, I got a little guy over here. I don't think I have enough cord to pull it into the camera, but I got a little lamp right here that if it's been on for too long and I go to adjust it by redirecting the lamp a little bit, I'll burn my hand because that thing gets super hot. Tungsten bulbs are black body radiators. You run voltage through them until the filament gets so hot, it burns brightly. That's the whole idea. But as a result, these fixtures, when you plug them in and they've been burning for a while, they get so hot that if you're not wearing gloves, you can't handle them without burning your hands. Okay. And that's something that LED fixtures just don't do. They're much, much more efficient with heat as a byproduct. And we don't burn our hands using LED lights. That's one of the reasons why they're so popular with filmmakers now. Their color's controllable and they don't get hot to burn your hands. Let's go to the other end of the spectrum and let's talk about CCT daylight balanced fixtures. Okay. daylight balance fixtures are meant to be used outside under daylight conditions as supplementary lighting for the sun, okay? Because the thing about the sun is it tracks across the sky. It's more intense at the midday than it is early in the morning or late in the afternoon. It'll change color quality early in the morning and late in the afternoon. And if it's a cloudy day, the intensity of the sun will vary greatly. If you've been out shooting outside and you have a clear day with, partly cloudy day, you'll notice that, your camera will take pictures pretty nicely in the open sun. Then the cloud comes in and covers the sun, and all of a sudden it gets notably darker and your camera has to be readjusted to accommodate that change. All right, so daylight sun is very unreliable in terms of it being consistent from morning, noon, and night. Problem with motion pictures is we work 12-hour days outside. So first thing in the morning when we're getting breakfast and we're setting up on set for the first shot, it might be before sunrise. And at sunrise, the sun's color is far different than it is at noon. First thing in the morning when the sun just peeks its head over the horizon, it's the same color as the lights that we use inside on stage at the studios, 3200 Kelvin. That's why sunrises look warm and goldeny in color, because low in the sky, the sun is at a different sort of photometric with the volume of the sky. The sky's a dome, right? And if the sun is directly overhead, the light rays can shine straight through and you'll get the high frequency light to strike you, and it appears daylight in color. But in the morning, at a different angle, okay, if you shine light through a dome, you'll see that it reflects and refracts at different angles down here than it does over here. And as a result, some of the high frequencies of light get scattered and bounce out of the atmosphere, and only the long frequencies of that light penetrate through and get all the way to your light meter or your camera on set. And that's why early in the morning, sunrise looks warmer than it does in the afternoon. And the opposite is also true at sunset. At sunset, during what we call magic hour, the last 30 to 40 minutes of the day, when the sun is sitting on the horizon the other side, it's really, really orange and goldeny in color again, because we're only getting the long frequencies to hit the camera lens. Okay. But here at noon, the sun's blue and white hot. Okay. So we need daylight balanced lights to work outside to help us sort of even out all those differences. And when the sun goes behind a cloud, we can either readjust the cameras and go through a whole fit of recalculation of exposure, or we can just turn on some artificial lights and fill in where the sun created shadows when it went behind the cloud. And when the sun comes back out, we either pan the lights away or we shut them off. Okay, so we need daylight balance fixtures outside, even though we're shooting with daylight, with sunlight. Okay. So let me ask you a very practical question based on what I just told you. If I'm shooting outside and I've been shooting at f8, let's say, ISO 200 at shooting slow motion, we're shooting 96 frames. Okay. Then the sun goes behind a cloud. If I have to recalculate all my exposure, I might end up at something like f4 as a result of that sun going behind a cloud. I'll lose a couple of stops behind the cloud, and then I'm shooting high speed, so I'm losing a couple of stops there. I might go from 8 to maybe a 4 out, outside, maybe a 2.8. Do I want to do that? If I'm shooting deliberately at f8 for whatever reason, and all of a sudden I'm at a 2.8, what problem do I have with my exposure and with my image? Something changed that I might need.
Can you repeat it again?
If I'm shooting something outside during the day and the sun ducks behind a cloud and I have to readjust my camera from say an f8 to a 2.8 or a 4, is that cause for concern? If I got to balance exposure by opening up my lens iris to something like a 2.8 or a 4, could that be a problem? Can you think of a situation where that could be a problem?
I would say
Yeah,
so.
it changes your depth of field.
I'm going to lose my depth of field, and
Yeah.
maybe I needed it. Okay. If I want to shoot at a 2.8 outside, I told you how to do it, right? We had ND filters to the lenses, and we picked 2.8 specifically for shallow depth of field. But if I'm shooting at an 8, could be because I'm shooting a car commercial, and I need all that depth of field to make sure that the hubcaps are sharp and the bumper's sharp and the guy inside the car is sharp. It's a commercial. I don't want to be at a 2.8 on a car commercial. I need all the details to be sharp so that the audience sees this shiny, beautiful vehicle that they need to then run out and buy, right? So if I'm at an 8 outside and the sun ducks behind a bunch of clouds and I'm shooting slow-mo and I'm doing all these things and I end up readjusting to a 2.8, that's going to blow my whole depth of fields plan out of the water, right? So that's another reason why I want to have my daylight balanced artificial lighting to use outside. When that sun ducks behind the cloud and it's no longer available, or it becomes late in the afternoon and the sun's going down and I'm losing available light intensity like crazy, I have to put light back into my images in order to maintain the same look and balance and tonal feel that I had around midday. And I need those daylight balanced lighting units to work outside now. And that's one of the reasons why I need lights outside. Logically, you would say, oh, I'm outside. I don't need to bring any lights for a photo shoot. Wrong. We need them as badly outside as we do inside. Okay. Here's an HMI bulb. Oh, hey, what happened here? Where's that from? Oh, that's from the other. Well, let me just do that. Here's an HMI bulb. HMI bulbs work a little bit differently than tungsten bulbs do. So in a tungsten bulb, we got this filament inside and it's heating up. We're running voltage through it and the resistance is making it heat up and burn orange in color. The HMI bulb, though, doesn't have any of that stuff going on inside. It looks like it's empty. Here's what's going on inside an HMI bulb, which is different than the tungsten bulb. First of all, you don't have a filament. There's nothing, there's two electrodes, an anode and a cathode, a positive and a negative, okay? And they are separated by what's called a spark gap, okay? So just these terms should tell you what I'm setting you up for. The HMI bulb is designed so that high current runs through one end of the bulb and jumps the gap to the other side to complete the circuit, and the light turns on. And this spark gap has to be maintained for as long as the light is turned on. And when you do that, it emits intensity. And that color value of that intense arc that's burning in here is very, very, very hot. And therefore, it burns very, very blue. And therefore, the color balance is more for daylight, which is why I made this sun a blue color. Daylight balanced. Now, the bulb is not empty. It's not just raw current jumping this spark gap in an empty glass jacket. There are gases inside of here that are designed to encourage that arc to happen in the first place. Flammable gases that when the current is introduced, the gases will ignite, the arc will be created. And as long as that arc remains unbroken, the current keeps flowing through that light, it'll keep burning and igniting the gas inside that bulb. And that's what gives us our output intensity and our color quality. It's a mixture of it's a deliberate mixture of gases, and it's called HMI for short. This is a label that Osram came up with. Hydrogenum medium arc iodide is the gas component inside this bulb. So we call it HMI for short because nobody can ever remember hydrogenum medium arc iodide. It's a tongue twister. HMI rolls off the lips. It's a lot easier to remember. HMIs are daylight balanced lights. Okay. They burn blue in color. And they were first developed by Osram. And in subsequent years, everybody has them now. We call everything HMI, even though Osram trademarked the term HMI. We call all of the daylight balanced fixtures HMIs. And then it's just a question of who made it. Airy, Mole Richardson, Sunray, Cinemills, K5600. There's a whole number of different companies out in Los Angeles that make daylight balanced motion picture lighting. Okay. The color discharge out of an HMI light is balanced to 5600 Kelvin, which is the daylight benchmark. Okay. 5600 Kelvin. And HMIs, just like tungsten lights, come in a variety of sizes. So this is a 575 watt HMI bulb. You can see how it kind of looks like a tungsten bulb, but if you look really closely in the center, you see a gas jacket and 2 electrodes and a big spark gap. Okay. That's how you know that that's an HMI bulb, is it's got this spark gap inside the gas jacket, inside the bulb jacket. Okay. This one here is a 1.8K single-ended HMI bulb. This is a double-ended HMI bulb. So current goes in one side and then leaps the gap and then leaves the other side and gets recycled through what we call a ballast. These lights are a little bit more like the way tungsten bulbs work. The anode and cathode are down here at the bottom, okay? And current goes in, jumps the gap, comes around on a thin wire that you can just sort of basically see running on the inside and returns here to the ballast. They all work basically the same way. They've all got a gas jacket and a spark gap in the very middle. Okay. This is a picture of 12,000 or 18,000 watt HMIs, daylight balanced fixtures, that guys on a crew like I used to run would use outside when we were shooting inside. So we're at a house, the location, we're shooting out on a patio by a pool, and inside the house in like the dining room and living room areas. The big guns, we call them, the big guns are outside, 12,000 watts, 18,000 watts, up to 24,000 watts each. And those are designed to mimic the intensity of the sun. They have the same color quality as the sun. And we use them outside to push through windows and things to light scenes happening inside using the windows, and the windows become our light sources. And then the big guns stay outside because they're so bright. You couldn't use these inside. It'd be like killing a fly with a shotgun. It wouldn't be, it's not practical. You can see how big they are. This guy right here is over 6 feet tall. And this light is making him look like a little dude. These are really, really big instruments. They're very large and very, very bright. We got other sources that we can use as well. Remember that old shop fixture in your dad's garage? Well, we can take those crappy old green looking tubes out of there and we can put in color corrected, photo correct bulbs for fluorescent fixtures. These are made by a company called KinoFlow, and they have bulbs that are balanced for tungsten 3200 or daylight 5600, and you just pick the bulb color that you need and you replace your existing crappy shop bulbs with these color corrected tubes, and now your fluorescent lighting is balanced to whatever setting you're using on your camera. KinoFlow, another company called Visions in Color, makes these kinds of bulbs as well. So we would do something like, we used to shoot at a studio in downtown LA all the time called LA Center Studios. And it's a big office building, basically, that has been converted for film shoots. There's no businesses that are in there full time. There's nobody in there that's doing anything other than making movies. So you go into an office on, say, the 10th floor of LA Center Studios, and you're going to film, say, a cop show. So we did Life on the 10th floor of LA Center Studios. And so the first thing that I did as the chief lighting technician on that show was, in pre-production, before we started shooting, I hired a crew to come in and change out all of the overhead fluorescent tubes, every one of them that were in there, hundreds of tubes, with color corrected tubes, so that when the cinematographer came in and turned the overhead lights on, they had the correct color balance that he could use them if he decided to shoot, to use them to shoot the episode with. And he could supplement with them from lights on the floor. He could turn them off. He could turn portions of them off and leave portions of them on. But he was free to use those existing fixtures with the correct colored tubes loaded into them. Okay. And usually what we'll do is we'll take existing fixtures like that in a house and we'll wire them up so that every other light can be turned on and turned off by the switches on the wall, right? So you might have 50 lights in a room in the overhead, right? On 2 circuits, one switch is every other row, and we would put 3200 Kelvin balanced tubes in those. And then the other switch, 5600 Kelvin balanced tubes in those. So you could turn off half of the room and have it be one color, or turn off those and turn the other half of the room on and have it be the other color. And then the DP has the flexibility of shooting under either color, depending on what suits the scene and what suits the lighting scheme that they're using. Okay. So we call the A-B lighting, right? A is one color, B is the other color. Okay. That's the kind of things that we would do before the age of LEDs. Now we can load the same tubes in every fixture, and then by controller, we can dictate what color comes out of that LED tube, whether it's orange or blue. So LEDs are making life even more complicated, but offering us more variables. So what is an LED? Well, an LED stands for light emitting diode. Okay. Light emitting diode. And all it is it's a little electronic device that works a lot like a light bulb. You're going to have a gas jacket. You're going to have a phosphor cap, it's called, which is usually at the top of the LED. And then you're going to have this anode and cathode frame, and it's going to have an electron gate in there, it's called. And that kind of works like the HMI bulb. So the electricity goes in through the cathode into the saddle, jumps the gate, goes down the anode. We create a circuit. And as it jumps the gate, it ignites the phosphor in the phosphor cap. And then that LED will burn with a predictable color. And so in the beginning, we had whole color LEDs, or blue or red or green LEDs. But as we started fiddling with the gas technology, a lot like the way fluorescent bulbs work, they have a gas inside that gets ignited. Sounds a little bit like an HMI bulb, doesn't it? Gases that get ignited and they burn a predictable color. Well, LEDs work basically the same way. There's a gas that's trapped inside the phosphor cap. When it gets ignited, it burns at a particular color. And so we have LEDs that are balanced for 3200 and LEDs that are balanced for 5600. Then we can use them in groups of what we call RGB or RGBA or RGBAW, where we use groups of LEDs and we combine the total output color to create white. Okay, remember, lighting is an additive process. We start from nothing, black, and as we add lights, we add intensity and color. And if we add all the colors of the spectrum in even amounts, the result is white light. The minute we start shutting off different frequencies, that's when the color of the light will apparently change to our eye and the hue will shift. All right, so if you have a red, a blue, and a green diode plus an amber diode and a W, a white diode, all 5 of those combined will give you perfect white output from an LED device. And that's the current technology that we're working with today. The behavior of the light in terms of color. This is the spectral response of the human eye as it responds to red, blue, and green, okay? The additive primary colors are red, blue, and green. Additive primary in terms of lighting, meaning start from black, add equal amounts of red, blue, and green, and the resulting value will be more intensity and white light, okay? A primary color is generally defined as a set of colors from which all other colors can be created. Okay. Different combinations of red and blue, different combinations of blue and green, different combinations of red, blue, and green will create all of the colors of the visible spectrum. And then depending on the system of your camera, 8-bit, 10-bit, or 12-bit, RGB is going to create 256 values or 1044 values or 1,000,000 and something values, right? Remember that from a few weeks ago? So when we're talking about primaries, we have additive primaries, red, blue, and green. We have the traditional primaries, which are a derivation of the secondary primary colors, and that's blue, red, and yellow. If you were to go to an art director or a production designer and say, what are the primary colors? He's probably going to say to you, everybody knows that, it's red, blue, and yellow. Because when you're mixing paint, when you're adding colors plus white, and mixing paint, you can create all the colors of the visible spectrum by using red, blue, and yellow. But when you're using light and starting from black, you have to use the additive primaries, red, blue, and green. And as you add them, you get white light. Okay. Then we have the subtractive secondary colors, which are a whole different mix of stuff. And that's what people that work in the printing industry use if they're creating books and posters and things. Using cyan, magenta, yellow, and black tint to create colors for textbooks or magazines, let's say. All right, that's the CMYK process you've heard about, cyan, magenta, yellow, and black, CMYK. And then we have tertiary color schemes, which use combinations of colors that are opposite one another on the color wheel. So you've probably seen this in art class from kindergarten on up. All right, depending on what kind of education you have given yourself. Liberal arts education, you've studied the color wheel several times over the course of your school career. So this shouldn't be new to anybody here, okay? But the notion is the visible spectrum, if you were to put it on a wheel, 360 degrees, you can see how certain colors are opposite others on this color wheel. And if it's opposite from another color on a color wheel, it's what we call a chromatic opposite. And if it's a chromatic opposite, it can be used to create contrast and perceive depth. Just take a quick look at one pair of very common, very predictable chromatic opposites, red and blue. You see how they are diametrically opposed on the color wheel? See that? Red and blue. Well, if we go back and we look at our color spectrum, they also happen to be at opposite ends of the color spectrum as well, right? Red and blue, opposite ends of the spectrum. Red and blue, foreground and background, right? If you start to think about these colors in this kind of relationship, you can start to pick values that will work nicely in a film frame as a compositional tool now. Warm colors in the foreground, cool colors in the background. Edge lights are always blue. Key lights are always orangish in color. And then we reverse that when we go outside. Okay. Or you can keep it the same so that your audience is never confused about what's happening in the foreground and what's happening in the background. It's really up to you, because we're going to start leaving the realm of science and traditional art and definitions and standards, and we're going to enter the realm of creative license, which means you can reassign or reinterpret the value and context of any of this, because it's a creative thing more than anything else. Whether something's red or blue is not going to affect your exposure necessarily. It's still going to be calculated the same way. F-stops and shutter speeds and frames per second. But a blue subject versus a red subject is going to have a very different psychological effect on your audience. So that's kind of where your creativity is going to start to come in. The way you play with color is going to open up a lot of creative avenues for you. Over here on the right-hand side are what are analogous, complementary, triadic, and split complementary combinations. These are color schemes that you can use. Art directors are real familiar with this kind of stuff right here. This is the kind of information that they'll use when they're designing sets, for instance. What color should I paint the walls? What color should I use for the wall hangings? What color should I make the furnishings? What color should I make the dresses and the hair and the makeup, right? Because they're using color. That's kind of their stock and trade in the art department, is color and saturation, and then we come in the lighting department and we use intensity and shadows for shape, softness or hardness of light. Then the cinematographer comes in and uses exposure for brightness and darkness balancing, right? And when all three of us work harmoniously together and we all kind of stay in our lane and we work the problem that we have in front of us, intensity and hardness and shape for lighting, color for art direction, and exposure for camera, man, we can do some pretty amazing things. Color has meaning. That's the last thing I want to talk to you about here. Color has meaning, right? Down here in the lower left are some things that we associate with these different colors. If I make this a little bit bigger diagram, you can see that there's at least one prevailing psychological ramification of color in each one of these color swatches. Yellow, happiness. This is a psychological underpinning to the color yellow. If you talk to Vittorio Storaro, he will lecture you at length about the psychology of color. This is one of his favorite subjects to talk about. Ad nauseum, this man will talk about color and what it means. Okay, but it's true, and it has a huge following. Psychologically speaking, certain colors are what we call provocative or calming. Yellow is a happy color. It's kind of skirting the provocative color range. Orange and red are provocative colors. Purple's a provocative color. Red is the color of passion. It's also the color of blood. Orange is supposed to signify friendship, okay? Well, blue over here might signify trust or loyalty. Green is wealth. It could also mean envy, right? We have this sort of dingy brown over here. That's comforting because it's an earthy, natural value, right? And we find Mother Nature kind of a comforting notion, right? Or we should. Comfort. Black is power. Black might also signify death. Okay. Black can also signify success or money, just like green. So if you're using a color scheme to describe an antagonist and the costuming and the environments are black and green, you could draw some psychological conclusions about that character just by the colors that were used to describe that situation. And the opposite could also be true for your protagonist. You're using blue and purple and orange as the color schemes for your protagonist. So there's friendship, trust, and royalty, right? Happiness. So how you use these colors might speak to your audiences on a level that is subtext to whatever your story is immediately on the screen. Okay, does that make sense? So that is as far as I want to take you in terms of color theory. That's not too deep in the weeds. The conversation can go a lot deeper if you want it to, but this is sort of an introductory discussion about it. Okay. We'll talk more about color when we talk about lighting, because lighting and color kind of work hand in hand. We talk about lighting and color a lot in cinematography too, as well, because like I said, it's one of those nonverbal communicative tools that we can use in our visuals that can help us tell a story to the audience, so we're not relying solely on the script. Okay, if the dialogue is weak or the action is not powerful, we can supplement a lot of those things with our visuals and help sort of get through the rough spots so the audience understands our message and receives our narrative affirmatively. Or if we want them to feel bad, they'll get that too, depending on how we manipulate these variables. It's all about sending a message to the audience. What do we want that message to be? And then using the appropriate tools in the predictable or appropriate fashion so that it elicits the response from the audience that we wanted. Okay. How do you feel about this topic? Any thoughts, ideas?
Not bad. Not bad.
Do you see any potential for any of this in terms of your creativity?
Yeah, I mean, I think there's a lot of potential. And I think it's seen in a lot of movies as of recent, the way filmmakers use color as maybe as like a hint to what the characters in their story may feel or what's happening in the moment.
Yeah.
I remember one of the Star Wars movies, the recent one, they did the red shade when Kylo Ren killed his father, to signify him going to the dark side, and sort of they played with the light on that, and I thought that was a cool effect.
What does the dark side symbolize?
Red, it's anger, hate. It's kind
Passion, yeah.
Anger, hate, passionate response to everything, right? So it's no mistake that Kylo's saber is red, is it?
Yeah. It's
And
a very
his
easy
grandfather's
example
saber
to
was
use
red
light
too.
color. Because blue is like good and red is bad. It's easy. It's an easy example of
Yeah.
And not only that, they made the Jedi as like trusting and knowledgeable. That's why they did the blue with the trust.
Yeah.
Yeah,
So
I just finished up a short film where we used a lot of purples and blues and grays and a little bit of red to kind of like symbolize like dark blues and purples we use more because it like gives off a sense of like fear and kind of like dreariness and then the anger as well and parts of the scenes as well.
sure.
That.
So you have all these different color. What I would love for you to do now, and it's not it's not an assignment or anything, but just for your own information, start paying attention to uses of color in the environment in all kinds of things. Okay, so Anakin Skywalker's saber when he was a Jedi was blue. When he accepted the dark side of the Force, his saber became red, or he changed to a red saber, right? Luke's saber was his father's, initially the blue one. When Luke transformed to the Force, he chose a green lightsaber. It's odd because here green indicates wealth, but on the previous color wheel, if we can look really closely, green also signifies nature, growth, fertility, freshness, health, safety, or money. So if green represents growth, then
It
Luke's,
shows that he's evolved as a character from the previous.
yes, right?
I was going to say too, it might be a wealth of knowledge.
Could be, yeah. Well, yeah. I mean, the same thing, right? Knowledge, growth is knowledge. It's a new awareness of yourself and your surrounding. Growth, right? His first saber was his father's, and it was blue. But when Luke came into his own power, that represented his personal growth and his new knowledge of the Force, and his saber became green, right? I mean, that's kind of sitting there right on the surface for you to find, but there's other places that you can find this. Did you ever notice that in the Marine Corps, all of their stripes of rank are red? Red is the color of blood, right? And that's kind of in their motto, right? Blood brothers, right? Semper Fi.
Their uniforms, their dress uniforms also have some lines, hints of red, which signifies blood too.
Accents of red, right? And when you graduate, when my brother graduated from Paris Island, when we all went to see him graduate, we had to wear a red polo shirt when we sat in the audience as a response to their rite of passage and their success as a graduate from Paris Island. We all wore red, right? So look at these symbols and these subtexts of uses of color in your in the world around you and see if any of them have a deliberate interpretive value, or if some of them just seem to be sort of random accidents. There's very few random accidents, right? What are the UCF colors?
Gold and black.
Gold and black. Happiness, but gold is even different from happiness. Gold is like success. And then you have black, power, nobility. It's certainly not death. I don't think, although some of you might not feel that good about your soon to be alma mater, but I think it's really more like the nobility, the success, and then with the gold, tinted with the gold, it's like a double whammy. It's to your success and to your nobility and to your future, right? And maybe in a weird way, it could symbolize death. It could mean the death of the individual who was uneducated and uninformed and unaware. And as you graduate, you become educated and aware. You enter a wider world. So it could be a weird death analogy after all, in a weird kind of a way. I don't know how the administration would feel about that interpretation, but it's certainly viable if you use color theory as the basis for your argument. So yeah, so these things are everywhere, right? Think about it, and think about all of this. And if you have any questions, feel free to shoot me an email or whatever. We can have a Zoom about it. We'll keep talking about this, like I said, when we deal with lighting, because it runs sort of part and parcel with lighting. On that note, I'd like you to read, I have, I think, 3 PDFs for you. Interesting reads, not very long, but they'll help reinforce this discussion. And then there's a chapter in the Brown Motion Picture Lighting for Video book on theory and control of color. And it's 20 pages in this little blue, the little blue looks like this here. I put it on your bookshelf. You've also got a downloadable tab on your reading assignment. It's The Lighting for Motion Pictures and Video by Blaine Brown. Okay, if you read that chapter, it'll explain to you lighting and color theory from the context of filmmaking, right? And see what you think of those things. There's no homework assignment for this week. I'm giving you a break. And then I'm going to hit you again with another assignment next week after we talk about 3-point lighting, okay? So again, I'll open up the floor to questions, and if there are none, then we can adjourn for the day. No one? How about questions about your homework assignment or anything that has thus transpired? Anything? Did you guys check out my my additional video on the worksheet? Did that help you gain any additional clarity on that exposure worksheet? Did you check it out? Probably just put that thing behind you and moved on, right?
I definitely need to go through that again because I thought I understood the exposure worksheet, but I was clearly way off.
Check it out. I put another video up. The link is in the announcements. And it's also on my YouTube page. You can just find it. It's the most recent, well, not quite the most recent entry on my YouTube channel. Okay. And it's just an additional explanation on the exposure worksheet. Supplemental, I think I call it, or that was the second one. This is an additional commentary. It's 30 minutes long, specifically on the solutions to the worksheet. So in my last one, it was a supplement, and I told you the framework and the thinking behind the worksheet and what you were going to do. The one I just put up the other night is the solutions to that specific worksheet and how I arrived at the solutions, and those solutions that govern the grades that you received on your paper. Okay, so the complete explanation of what you got wrong is there on that video if you are interested. Okay. And if you got any questions about that, again, shoot me an email. Okay. I don't want you to walk away and just go, I don't know, the hell with it. We can hash it out if it's, if it's something that you really want to work out and make sure you understand it. Cause I think it's helpful no matter what discipline you're going to work in when you get out of here. Okay. So let me know if I can help you in any way. Otherwise, that's it, folks. So thanks for your time and your attention. I appreciate it. Have a
Thank
good afternoon. And I will not see you guys until next week. So have a good week, and I'll talk to you next Monday. Thanks a lot.